This podcast is for 3.7, graphing linear functions. The first example says evaluate the function h of x equals negative 7x when x equals 7. So for a problem like this, you're going to be plugging in x for, or plugging in 7 for x. So I am going to write h of 7 because in here is where I'm going to be showing that I'm solving for a value of x of 7 equals negative 7, and then I'm going to plug in my 7 to solve. So h of 7 equals negative 7 times 7 is negative 49. So try an example like this. G of x equals 2x plus 5 when x equals 3. For the function f of x equals 2x minus 10, find the value of x so that f of x equals 6. So this one's going to be a little bit reverse. Now it's saying f of x equals 6. So that means I'm going to plug 6 into there to solve for x. So 6 equals 2x minus 10. Add 10 to both sides. Divide by 2. So x equals 8. So when f of x equals 6, x equals 8. Go ahead and solve this problem for the function g of x equals x plus 3. Find the value of x so that g of x equals negative 2. Story problem. The gray wolf population in central Idaho was monitored over several years for a project aimed at boosting the number of wolves. The number of wolves can be modeled by the function f of x equals 37x plus 7, where x is the number of years since 1995. Graph the function and identify its domain and range. All right, so on this slide, what I did was I created a table and a graph. Now, on my table, I plugged in just 1, 2, and 3 to help me with my graph. And I plugged it into the equation that they gave me, f of x equals 37x plus 7. So I plugged in values 0, 1, and 2 to solve for my y values so I can plot points. So looking at my x values, now the reason why I chose 0 is because looking at my graph, you cannot have a negative number of wolves, and we're talking about years since 1995, so I don't want to do any years before that. Okay, so on 1995, when I plugged in 0, I got 7. So I graphed 0, 7. When there was 1 year since 1995, there were 44 wolves. So I plotted 1, 44. My second year past 1995, plugged in 2, and I got 81, and so on. I kept the same graph. Now, you could have used slope-intercept form to graph, so you would have plotted your first point at 7, and then you would have used the number in front of x to do up 37 to the right 1. So up 37 to the right 1 would have got me the same point. All right, now it's asking for domain and range. Now, remember the domain is my x values. So my x values, here is my x-axis, start at 0 and increase. So to show a domain that starts at 0 and continues to increase, I would say x is greater than or equal to 0. Now for my range is my y values. My y values do not start at 0 because this point is not 0 for my y values. My first y value that is listed, when I plugged in 0, right here in my first situation, I got 7. So this point is 7. So y is greater than or equal to 7 because it keeps increasing from that point on. All right, the next part of this lesson is over vertical transformations. The first part is a translation. Now, we are going to be comparing our graphs to the x graph. Now, the x graph, if I had y equals x, which f of x equals x is the same thing, if I plugged in 0, y is 0. If I plugged in 1, that's 1. So when I plot my points 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, etc., I'm going to plot that first line. Okay, and I want to compare it to the graph g of x equals x plus 1. Now, this is probably going to be helpful if you use different colors for your graphs. I'm going to use slope-intercept form. So my first point is going to be up to 1. And then my slope is 1 over 1. So it's the same slope as the other one. So it's going to run right along the side of that one. And my last graph, this graph, b value is -3, so I'm going to go down here to 3. Same slope though, so up 1 over 1. We had talked previously about how when graphs have the same slope, they are parallel, so this is showing that as well. All right, so let's compare our g of x and h of x to, this is called our parent function. The green is my parent function, when f of x just equals x. So let's look at g of x. G of x is parallel, has the same slope, however, it is translated up 1 unit. So instead of my graph starting at 0, like my g of x was, it is translated up to 1. So I'm going to say g of x translates up 1 unit. Okay, now my h of x, compare that to your parent function. So h of x, if I take it from this 0 point, it is translated down 3 units. So h of x translates down 3 units. Okay, so when we see a shift of the line just moving up and down, it is called a translation. And what occurs in a translation? If our b value increases, the graph is translated up. If our b value decreases, the graph translates down. So you can see this happening in the example. All right, now a rotation. When the slope m is changed in the function f of x equals mx plus b, it causes a rotation. So let's compare graphs on this one. I'm going to start off with my parent function again, because we always want to compare our graphs to our parent function. So 0, 0, 1, 1, 2, 2, 3, 3. So a linear parent function is f of x equals x. All right, now I'm going to g of x. G of x equals 2x. Okay, now I'm going to rewrite it, 2x plus 0. So I still have the same y-intercept, so I'm going to plot my point there. However, my slope is 2 over 1 instead of 1 over 1 like it is in f of x. So I go up 2 to the right 1. Up 2 to the right 1. Down 2 to the left 1. Okay, so that's g of x. And now h of x. Again, I could say plus 0, so I still have the 0, 0 point. Now my slope is 1 over 2, so up 1 to the right 2. Up 1 to the right 2. Plot this point. Okay, so let's compare these graphs to f of x. Now, if you look at the graph in red, which is my g of x, let's look at the slope. The slope is 2 compared to my parent function, which is 1. So what happened was my slope increased from 1 to 2. So when your slope increases, the line becomes steeper. So you increase the slope, the line is steeper. Now just the opposite, if you decrease the slope up until you get to 0, the line becomes less steep. So h of x is less steep, and g of x is steeper. Okay? So the big points is to look to see that a translation is when the b value changes, and a rotation is when your slope changes. All right. Sometimes you have a slope that changes to a negative. Now, when a slope changes to a negative, we have learned that when Joe climbs the mountain, it is a positive slope. So if Joe goes down the mountain, it is a negative slope. So we have learned that the slope completely changes from an increase to left to right to a decrease from left to right. Now how that happens is, again, a negative slope. And we call this type of transformation a reflection. So when the slope m is being multiplied by -1, and f of x equals mx plus b, the graph is reflected across the y-axis. Okay, so again, I'm going to compare my graphs to my parent function. Okay, so here is f of x. G of x equals -x. Now, again, remember it's -1x plus 0. I just rewrote it. So -1x would mean I go down 1 to the right 1. Down 1 to the right 1. Okay, so this would be my g of x. And then my h of x is -3x plus 0. So again, 0, 0, but this time I go down 3. 1, 2, 3. And to the right 1. 1, 2, 3, to the right 1. So you can see that when we change our slope to a negative, that we have a slope that is reflected. Also on h of x, my slope has become a 3, so it is becoming steeper. So h of x is reflected and is steeper than my parent function. Okay, so when we're looking at steepness, we always want to look at the absolute value of the slope. So if the slope was -3, like what it is in h of x, the slope, we're going to look at the absolute value, it is 3. That is an increase from my parent function, which has a slope of 1. So that shows that it has become steeper. All right, go ahead and try these next 3. Again, we are comparing these to our parent function. Now, sometimes there's only going to be one thing occurring to a graph. Sometimes there might be multiple things. So go ahead and try these on your own. That concludes the podcast for 3.7, Graphing Linear Functions.